continue. Okay, great. All right, so what we're going to do today is we're going to wrap up the discussion of molecular orbitals. So yesterday's video was kind of short. It was only about 25 minutes or so. I just wanted to give you sort of a background on molecular orbitals, where they come from. And then what we'll do today is we'll look at some of the ALEKS problems, okay? So let's begin just quickly. The idea is that when you're dealing with molecular orbitals, and we'll call those MOs for short, these are what happen when you take an atomic orbital, AO for atomic orbital, and you add them, so I'll call this AO1, to each other. All right, so notice I put plus or minus, right? Because we're going to take the constructive interference, which is plus, that's additive. And then we're going to take the destructive interference, which is the negation, it's negative, okay? So remember, think about it this way. Subtracting a number is the same thing as adding a number that you've changed to a negative, right? Change the sign of it. So we're going to add and subtract these two atomic orbitals. And in general, here's what happens. You get two new orbitals, which are called molecular orbitals. And so the difference is, now this is two different atoms. So here's your nuclei. The difference is that in one of them, you get a new orbital that has zero amplitude or zero probability. We call that a node in between the nuclei, right? So those two atoms are really not bonded to each other with this new orbital. And so any electrons that are in that orbital are not bonding. We call these antibonding. So this is an antibonding orbital. And that corresponds to the minus. You're subtracting them. And remember, we use a star. So it could be either a sigma star. In general, that's what a sigma star looks like. Okay. So the star is what tells us it's antibonding. So when you see that symbol, it's an asterisk. That means it's an antibonding orbital, okay? The significance of that orbital is that it's higher in energy than the atomic orbitals. So any electrons that go in there tend to destabilize the molecule or the ion, okay? Now, you also get the addition. The addition is different, though. You have, here's your two nuclei. Now you have a lot of electron density in between the nuclei. So here's your new orbital, right? There's a little bit of it out here, and there's a little bit of it out here, but it's mostly confined to in between the nuclei, and that acts like a glue. It holds the two nuclei together, and we call it a bonding orbital. And we just, this would be a sigma. This would be a sigma orbital. Okay, so any electrons that go into a bonding orbital tend to stabilize the molecule. The molecule is more stable if it has electrons in the bonding orbital because they're holding the two atoms together. And you can do an analysis of more complicated molecules. You can do 5, 10 atoms. The problem is molecular orbitals, in order to really analyze them, it requires enormous amount of calculations that require supercomputers. So even today, even with our really fast computers, it takes a lot of effort to calculate these molecular orbitals just because of the complexity of the mathematical functions that make them. But it's doable, and it is something that people will do. However, here's another issue, which is that if it requires a supercomputer, how good is it for us in everyday analysis? Like if we're doing something every day and we're trying to analyze energies and structures and all of that, how useful is it if it requires a supercomputer to compute it? And the answer is it's limited. It's of limited use on a day-to-day basis. So for the most part, working chemists will use Lewis structures, hybridization, which is valence bond theory, and less of the molecular orbital theory. However, if someone is really trying to analyze a molecule in great detail, then molecular orbital theory is probably more accurate. It actually explains things probably better than for most things than it does for valence bond theory. Okay, so let's get to the issue. Now, I said that there were essentially bonding and antibonding, but remember, we also said that if you take a p orbital, so let's say you take a 2p and you add it to another 2p. So this is from atom A and atom B. This is all from yesterday. Again, you get different possibilities. So one is you have a bonding orbital that looks like this. So this is a bonding orbital. And then this would be a sigma that's from a 2p. And then you can also get an antibonding orbital. So it looks like this. And then we're going to call that a sigma star 2p. Okay, that's what you get. So again, here's your node. That's what you get when the p orbitals are pointing directly at each other. So that's the case. This is the case right here where the first one, this orbital, this 2p, is directly lined up with this 2p. Okay, and a reminder again, we said that if you can draw a line through both nuclei and through the orbital, then it's a sigma. That's how we define a sigma, that you can draw a line through both nuclei and through the orbital. Okay, so this is your star because it's antibonding. But then we also said for the 2p that they may not be pointing toward each other. So you can also have this situation where they're actually like this. They're parallel to each other, but not pointing at each other. And that leads to an interesting result. So what happens there is you get this new orbital, which is a bonding orbital. And it's a bonding orbital because there's no node here, right? So there's electron density in between the two nuclei, but it's above and below. Isn't that crazy? It's above and below the two nuclei. It actually has two regions. And so we call this one a pi 2p, meaning it came from a 2p orbital, mixing 2p orbitals. And it's a pi. So if it comes from p, we call it pi. If it comes from s, we call it sigma. But the idea here is you cannot draw a line through both nuclei, a straight line, through both nuclei and through the orbital, right? The orbital is above and below where the nuclei are. So you can't draw a line through all three. So we don't call it a sigma. Sigma is when you can draw a line through both nuclei and through the orbital. Okay. And then you can get an antibonding as well. So the antibonding, I'll draw that to the right here. This one's cool looking. It actually has a lobe out here, a lobe out here, a lobe. People draw these differently, but there's 4 lobes. But notice there's a node again, right? When you see that node and you see the orbitals are kind of pointing away from the nuclei, that's an antibonding orbital, just like this one. They're pointing away from the space in between the nuclei. People do draw them slightly different. So anyways, this one's a pi. Again, you can't draw a line through the orbital and through both nuclei, so it's a pi. It comes from a 2p, and then it's an antibonding orbital. Okay, so this destabilizes. We'll talk about the energies of this in a moment, but I want to look at the first Alex problem, which is a very simple problem. All they do is they ask you to count the number of sigma bonds, so that'd be a sigma, and the number of pi bonds in a molecule, sigma and pi. And that's a very common thing we do in organic chemistry. When you go on to take organic, if you do biochemistry or cell biology, sigma and pi bonds describe organic molecules really well. So let's take a look at a new one. At a problem. So here's the issue. So they're going to have you count. So here's what they do. They give you a structure. They give you the Lewis structure. It's organic. So this one has 3 carbons. And you can do this for really large molecules. There you go. So there's your Lewis structure. And what they want to do, they want you to count up the number of sigma bonds and the number of pi bonds for the highlighted atom. Okay, so for the atom that they've highlighted. So let me do this. For this particular one, they highlight this atom here. So let me highlight it. Oops. There you go. So there's your highlighted atom. So 1, they want you to know the number of sigma bonds for that atom, the number of pi bonds for that atom, and then a little bit of review. They want you to tell us the orbital hybridization. So that's not molecular orbital. That's actually hybridization, which was the earlier section, which is valence bond theory. Okay, so that's section 9.5, but they do ask you to do that too. So it's a good idea. Because again, as I said, organic chemists, most chemists on a working daily basis will deal with hybridization more than they'll deal with molecular orbitals. Okay, so let's do it. So it's just this one in red. So here's what you do. It turns out, and we'll see this in a moment, that if you have a bond between two atoms, that bond is always a sigma. And there's a logic behind it. It turns out a sigma bond is stronger than a pi bond. So if two atoms are attracted to each other, they're going to use the orbitals that give them the strongest bond, which is always a sigma, which just means they're pointing at each other, right? Really, a sigma bond is what happens when the orbitals are pointing directly at each other. So whenever you see a single bond, that bond is going to be a sigma bond. If there's more than one bond between two atoms, then the first one is sigma. Any additional bond will be a pi bond, any additional. So if you have 3 bonds, the second and third bond would be pi bonds. The reason for that is that if you have a sigma bond, the orbitals are pointing at each other. So now you got this new molecular orbital. That space is taken up. There's no more room in between the atoms. So the only other bonding that can take place is the bonding between the p orbitals, which are pointing 90 degrees apart from each other. So that's going to give you a pi bond. And then you can rotate out another 90 degrees towards you. Remember, space is 3-dimensional, right? So first one's a sigma, second one's going to be a pi, third one's going to be a pi, and there's your triple bond. Okay? If you only have a double bond, then you're going to have a sigma for your first bond and then a pi for your second bond. But if you only have a single bond, it's got to be a sigma bond, no pi bond. Okay? So for this one, it's pretty simple because that particular atom, it doesn't have any double or triple bonds. It only has single bonds. So every single bond has got to be a sigma bond pointing directly at each other. Okay? So this has got to be a sigma. This has got to be a sigma. This has got to be a sigma. And so does that one. So this one actually has 4 sigma bonds, that particular atom. Now the atom next to it, the carbon next to it, I'll do that separately. I'll do that, even though the problem doesn't ask you for that, I'll do that in a moment. The number of pi bonds, there aren't any because that particular atom doesn't have any double or triple bonds. So it doesn't have any. Okay. And then orbital hybridization, let's do that. Remember how we did hybridization in the previous section? What you did was you looked at the number of electron domains, and then that gave you a hybridization. So if it had 2, that was sp. If it had 3, that was sp2. And if it had 4, that was sp3. Now for carbon, you're not going to have any higher hybridization. It's not really possible. But if you're dealing with third row elements, then you can deal with these, right? So I'll put a little box around that. That's only good for third row elements or fourth or fifth, right? It's not good for second row. Okay, so if you count up the number of electron domains in this particular atom, it's 1, 2, 3, 4. So that's 4, so that's sp3. So now we know that particular carbon atom is sp3 hybridized. It is more difficult to break a sigma bond than it is to break a pi bond in general. Pi bonds are easier to break because they're weaker. And so for that reason, that carbon atom should be pretty stable. It should be hard to break any of its bonds. In fact, the carbon-carbon single bond is a very difficult bond to break. It requires a lot of energy to break that chemical bond. And so they use it, they do break them in chemical refineries where they make petroleum, where they make them not. They take petroleum and turn it into gasoline. So gasoline molecules tend to have like 5 to 10 carbon atoms, really like 5 to 8. No, 5 to 10. But when you get crude oil, many of the molecules have more than that. So it's not useful as gasoline. So what they have to do is they have to break the molecule apart. And that's called a cracking plant. And so you have to break those bonds. Cracking, they call it. Now let's try one of the other carbon atoms. I'm going to erase this one here. And let me make this one in blue. So let's try that one right there, that carbon atom there. Let's look at that one, okay? So that carbon, let's do the number of sigma bonds. Now take a look at it. It's got a triple bond, right? That's a triple bond. And then it also has a single bond. So what I said was if it's a single bond, that's a sigma. Right? In fact, we already figured that out, right? That bond is a sigma. We already figured out for the other carbon atoms. So that's a sigma. Then we said that if you have more than one bond between two atoms, the first one is going to be a sigma. And then any additional will be pi. So this one right here is going to be a pi bond. And this one right here is going to be a pi bond. So for that carbon atom, you've got 2 sigma. And then you've got 2 pi. And then it's going to have a very different hybridization, right? That one right there, that carbon atom, it looks like it's only got 2 electron domains, right? Because it's got a single bond to the carbon in red, and then a triple bond to the nitrogen, so that's only 2 electron domains. So for that carbon, 2 electron domains is sp. So that one's sp hybridized, okay? So in general, the way we think about, I mean, really, in a sense, the reason we're concerned about sigma and pi is that pi bonds are easier to break. So a chemist, if they're looking at reacting something, they're going to look at initially at the pi bonds. The pi bond, like if you look at this organic chemical and it breaks, it reacts. What you do is you look and see, does it have any pi bonds? Because pi bonds are easier to break. So maybe the pi bond broke. So in this particular carbon atom here, there's a couple bonds that might be, susceptible to breaking because they're pi bonds. Now, why are they weaker? Here's the idea. When you have 2 atoms, the first one is a sigma, right? So sigma bonds point directly between the 2 nuclei. So those electrons are really close to the nucleus. They're close to both nuclei. So that's going to be a very strong bond. That's a sigma. Whether it came from a S or a P, it doesn't matter. The sigma ones are strong because they're pointing directly at, they're in between the 2 nuclei. But a pi bond, that's going to be up here and down here. And so the amount of, remember we talked about this with valence bond theory, the amount of overlap is not that great. In fact, let me show you what I mean by that. If you take a 2p orbital and another 2p orbital, right? That's a 2p and that's a 2p. There's not much overlap there. They're pretty far apart from each other. So the amount of overlap is pretty weak. So they're going to be weaker. Weaker means easier to break. Stronger means harder to break. So because in this particular orbital here, oops, sorry, let me erase that. There we go. If they're pointing directly at each other, there's a lot of overlap. So that one's going to be strong. So for that reason, this will be a strong bond. This will be a strong bond. This will be a strong bond. But these other ones, these pi bonds, are going to be weaker. Okay, so that's the first type of problem with that you have to do. The second one is recognizing orbitals. That's kind of fun too. So here's what they do. They show you a molecular orbital. So here's your nuclei. And then they kind of draw it like this. See, they draw it a little bit differently than I do, but pretty similar, right? What you want to do is you want to look here. If you see a space here where there's nothing, that means you have a node, 0 amplitude. So there is no wave density right there. So what they do is they ask you to write the symbol for the MO, for the molecular orbital, okay? And then they ask you, is it bonding or antibonding? And then they ask you, is the energy higher than compared, sorry, to a 1s orbital or lower? Okay, so there's 3 questions here. So that third question actually gives you some good information that's going to help you kind of solve this problem. So if you look at this molecular orbital, first of all, you can see there's no density there. So it's definitely an antibonding orbital right there, right? If it was a bonding orbital, there'd be no space in between there. Okay, so right there, that tells you that it's antibonding. Now the only question is, really, is it a sigma or is it a pi? And remember, the pi, you cannot draw a line between both nuclei and the orbital. But for this one, you can. Okay, so you can actually do this. You can just draw a line through the middle of the orbitals, right? You're going right through the center of the orbitals and you're going through both nuclei. That's a sigma. That's what a sigma bond is when you can draw that line. And then finally, is this higher energy compared to a 1s? So if you're looking at the energy of the 1s orbitals, how does the energy of this thing correspond? Now, I looked at that a little bit yesterday, so if you don't remember, you can always look back to that one. But essentially what we said was this. When you are, so this is for, remember I said for hydrogen. I'm sorry, hydrogen. Okay, the molecular orbital, we're taking 2 atoms. What we said was, if it's a bonding orbital, it's going to be lower in energy than the energy of the atomic orbitals, right? These are the atomic orbitals. This is the molecular orbital. So if it's a bonding orbital, it's lower in energy. That's why the molecule forms, is because the electrons are just going to pile in there. And now it's lower in energy. The hydrogen molecule, H2, has less energy than 2 separate hydrogen atoms. That's a pretty amazing thing, but that's why we have molecules in nature, is because sometimes the molecule has less energy than the individual atoms under some conditions. So on the Earth, in general, a hydrogen molecule has less energy than 2 separate hydrogen atoms. So they react. And here's our molecular orbital diagram to show that. Now, we also said the antibonding orbital is higher in energy. So this is sigma 1s star. So this one's higher in energy. So that what that means is if the electrons go up here, the molecule has it's higher, it has more energy than it did as individual atoms. So that would destabilize it. It would be unstable, right? So, you never see a rock fall up a hill. You can throw it up a hill. You can give it energy and make it go uphill, but you never see a rock fall up a hill. It always falls down, right? The reason it falls down is that when it comes down to the lower energy, it has less potential energy, right? That's essentially driving it. So the same thing here. The electrons are not going to fall up unless they have to. They're going to fall down. And so that means the molecule is going to be stable. Okay, so the answer is the energy of this orbital, because it's an antibonding, right? That's antibonding. That's going to be higher in energy than the atomic orbitals. So what you're doing is you're saying, hey, it's this one up here. It's antibonding. We already know it's antibonding because there's this node here. So that means that it's going to be higher in energy. Okay. Let's take a look at another example. Okay. Okay, so this one is telling you it's formed from 3p orbitals. Okay, and then they show you a picture. Okay, and then you want the symbol. And then you want to know, is it anti or is it bonding? And then you want to know, does it have higher or lower energy than the 3p orbitals? Okay. Now, the only question I have is when you do the symbols, do they want you to put the asterisk? Oops. Let me just see here. Okay, so they do want you to, they want you to write the full symbol. So let me show you how to write the full symbol for this so that you get this right, okay? So first of all, I'm gonna do the second one. I think it's easier if you do this one right here first, okay? So is it anti-bonding or is it bonding? Well, again, what you wanna do is you wanna look between the nuclei. Here's your nucleus for the second atom. Here's the nucleus for the first atom. See how there's empty space here? That's the giveaway that it's an anti-bonding orbital, because what that means is the electrons are essentially pushed away from the space in between the nuclei. If it's away from that, that means it's anti-bonding. Okay, so this one right here is anti-bonding. Now, the next thing you want to do is you want to determine, is it a sigma or is it a pi? And again, the way to do this is just draw a line between the nuclei and ask yourself, does the line go through the orbital? Like, is the orbital actually centered on that line, centered around that line, right? So here's the idea. If you had something that looked like this, that orbital is centered around the line. But here, the orbital is above the line and it's below the line. It's not centered on it, okay? So that means that it's a pi bond, right? So sigma is determining by that line, pi, that means that it's not around the line, okay? So that means it's a pi bond. So that means we can write a pi. Okay, you're going to have to probably use the little, the little menu that comes up where you put in symbols. So it's a pi. Now I want to show you the full thing here. Since we already determined it's an antibonding orbital, you got to put the star. Okay, so since it's antibonding, you got to put the star. And then the notation of molecular orbitals is that not only do you tell what kind of bond it is, you indicate what orbitals it came from. So this particular one came from 3p orbitals. Okay, so you write that as a subscript. So you put the 3p as a subscript, you put the antibonding as an asterisk, and then whether the line goes through or doesn't go through all three, that's going to tell you whether it's sigma or pi. So the overall, this would be pi 3p star, meaning it's a pi bond, it's an antibond, and it came from 3p orbitals. Okay, interesting. And then the last question is this higher or lower? That's simple. It's always the case that you take your AOs. If it's bonding, it's lower. If it's anti-bonding, it's higher. Okay. So since we already determined this is anti-bonding, it's higher in energy. Okay. And you can make these molecules do cool. I mean, you can take an electron that's here, put in a photon, and promote that electron up to here. You can actually measure those things. So people do that. And so in fact, I think oxygen, O2, it actually does that. Like if O2 is a liquid, is slightly blue. It has a blue tint to it. And you have to liquefy it, right? So they use that for rocket fuel. Liquid, it's actually the oxidant. It's not the fuel itself. But liquid oxygen is used in rockets. And it has a slight blue tint to it. And that blue tint is due to the fact that there's actually there's actually an orbital. I think it's a pi, and then you can make it go to a pi star. So you can make the electron go up to there. So there's your electron going up there, and there's photon, right? Photon comes in, and so that photon has the right amount of energy, and that makes the thing appear blue. Essentially, the photon is red, so when you look at it, that red photon has been absorbed, so it looks blue to you. Okay. All right, so there's that one. The next type of problem is now about doing the energy diagrams. So let's talk a little bit about energy diagrams. Okay. Now, as I said, these energy diagrams, they have to be calculated using molecular orbitals. So here's essentially what happens. If you think about it, you've got, 1s orbitals, 2s orbitals, 2p orbitals. Remember, there's 3 of those. 3s orbitals, 3p, there's 3 of those. 4s orbitals. Then you got your 3d orbitals, there's 5 of those, right? So there's a lot of atomic orbitals in atoms. Now, we're just going to deal with period 2. So we're just going to be concerned with lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine. But again, these are molecular orbitals, right? So that means we're going to deal with the molecules. So F2, O2, N2, C2, B2, Be2. These are the second period. So notice we're really only doing simple molecules. We're not doing big organic molecules. We're not doing even Br2 or Cl2 or HCl even. The reason for that is these molecular orbital diagrams get really complicated if the molecule is complicated. Even Cl2 is more complicated. So we're only going to deal with what they call diatomic molecules, meaning molecules that have 2 atoms. They're also only going to have the same element. So we're not even going to do like HBr or HF. We're just going to do Li2 or Be2. But we are going to add one issue of complexity. We're going to also look at ions. So we're going to look at those molecules and their ions. So you could do, for example, F2 minus or O2 minus or B2 plus. So we're going to look at the diatomic molecules, but also ions, because just to make it more interesting, to be honest with you. There's no reason we have to do that, but it's just to make it more interesting. So here's what you're going to do. They're going to ask you to draw the energy level diagram. For a molecule or ion. Okay, so it might be F2, for example, that would be the molecule. Or it might be F2 minus, which would be the anion. That would be the ion, okay? Now, in order to solve these, you have to refer to these diagrams that Alex provides them, but your textbooks also provide them. So I'm gonna, let me end the sharing here. And let me bring up, here we go, share screen. So let me bring up, here we go. Okay, so hopefully you can see this right here. This is a molecular orbital energy level diagram, okay? So I want you to take a look at it. What you'll see Let me see if I can bring this around a little bit. There we go. So centered it a little bit better for you, right? So this particular diagram shows you how you add the atomic orbitals for two atoms to make the molecular orbitals. So notice there's orbitals on the left side, AOs, and there's orbitals on the right side, AOs. Those are the atomic orbitals that we're mixing from two separate atoms. Again, they're going to be the same element. So it's not going to be like HCl or HF. It's going to be H2 or F2 or F2 minus. So each atom has to be the same element for the ones that we're doing. Okay. So the one on the left could be the first atom and the one on the right would be the second atom. And then this shows you how they form the molecular orbitals. And it's that center that you want to pay attention to, because that's the energy level diagram for the molecular orbitals. So notice the order. The one that's at the lowest is sigma 1s. Above that is sigma star 1s or sigma 1s star. So that's the bonding orbital that you get when you mix the 1s orbitals, and the antibonding orbital when you mix the 1s orbitals. Then in the second row of elements, there's also 2s2, 2p something, right? So you've also got the mixing of the 2s orbitals. So you get sigma 2s, right? The 2s refers to the orbitals it comes from, and then sigma star 2s. So that's the antibonding orbital, just like we've talked about. Then you get up to the 2p orbitals. The 2p orbitals start to mix. And so you get a pi 2p and then a sigma 2p. So notice you've got three orbitals that are lower in energy than the 2p orbitals. There's two for the pi 2p and one for the sigma 2p. So that's three orbitals. The number of orbitals you put in as atomic orbitals has to equal the number of molecular orbitals you get out, just like we did with hybridization. And then you've got antibonding orbitals that are higher in energy. So there's a pi 2p star and then a sigma 2p star. So you wouldn't be able to predict that order easily. That order is coming out of supercomputers, right? And it's, you can experimentally test it, but that's not something we can just figure out. That order, that diagram comes out of a calculation. So that's why I wouldn't recommend memorizing it if you don't want to. Just make up a card and have it next to you when you do these problems. Okay. So in general, though, antibonding orbitals are higher in energy than bonding orbitals, right? And keep in mind that the number of orbitals is conserved. So if you look at the atomic orbitals, we have, 10 of them? 1s, 2s, and then there's 3 for the 2p for each atom, so that's 10. If you look at the molecular orbitals, you got 10 orbitals, okay? So in general, bonding, if electrons are in bonding orbitals, that stabilizes the molecule or ion. If the electrons are in the anti-bonding orbitals, that tends to destabilize the molecule or ion, okay? Now, this diagram is only good for lithium, beryllium, boron, carbon, those first four elements of the second row. The second, and nitrogen. And nitrogen. For oxygen, fluorine, and neon, there's actually a different diagram. So let me show you the different diagram. It is, let me stop sharing. And then let's share. So I gotta find the right one. Is it this one? No, I'm sorry, that's the wrong one. Oh no, that's it. Okay, so this is it. So this one is called Molecular Orbital MO Energy Level Diagram for 6A. That's group 6A. So this one's good for oxygen, fluorine, and neon. So the other one was good for the first 5 elements, lithium through nitrogen. This one's good for the last 3. So there's only a slight difference, but it's an important difference. If you look at this one, essentially what has happened is the order's been changed. So now it goes sigma 2p, I'm sorry, sigma star 2s, then sigma 2p, and then pi 2p, pi star. So notice way up here at the top, the pi and pi star for the 2p's are right next to each other. That's the difference, okay? So these diagrams are important because you in these problems, you're going to need to fill them out. You need the Aufbau principle. So you got to use the right one. So if it's group 1A through 5A, use the first one. If it's group 6A, 7A, or 8A, 6 through 8, then use the second one. Okay, otherwise you'll get the wrong answer for some things. So let me stop that one right there. And let's come back and share this one here, and I'll show you a problem. Okay, so they want us to write the energy level diagram for F2 minus. So this is the first Alex problem that I saw. So that means you're going to use the second diagram. So immediately what you want to do is you want to, I'm going to draw it out here. It's vertical. Generally, these are drawn vertically. So it's sigma 1s, sigma 1s star, sigma 2s, sigma 2s star, and then it's sigma 2p, and then it's pi 2p. I'm sorry, I'm running out of room here even. So let me do this again. It's kind of annoying. I don't like doing things vertically, but most of the textbooks are going to do this vertically. So let me just show you. So it's 1, 2, 3, 4, 5. So there's a lot of orbitals, right? And then you get these here. There we go. So for me, it's easier just to write it that way. So then you got to write. So the notation is kind of annoying because you got to use Greek letters. Okay, so there they are. All right. Now, one of the things that I kind of disagree with, but some textbooks do this, is they include the core electrons in this calculation. And I guess there's a reason for that. The core electrons, in theory, are involved in interactions. So here, be careful with this. In Alex, they're going to have you start all the way at 1s. That's actually core electrons. Remember, for fluorine's in the second period, so really that's shell 2. So they're going to require that you include all of the electrons in the atom, not just the valence electrons. So be careful with that. So what you do is you say, hey, fluorine is element number 9. So that means it has 9 electrons. It only has 7 valence, but it has 9 electrons. It's F2. So F2 would be 2 times 9. That's 18. Then it's negative. So F2 minus would be 18 plus 1, which is 19 electrons. Okay? Now, here's what you do. Aufbau principle, just like you did for atoms when you were doing like iron or nickel or chromium. You just fill out. Each orbital can have a maximum of 2 electrons. And you just fill it out until you're done with the electrons. We got 19 to do. 1, 2. Remember Hund's rule that if you have orbitals at the same energy level, you do spin up, and then you pair them up, spin down, spin down. Same thing here. That's a rule of quantum mechanics. So 1, 2. Okay? So how far have I gone? 2, 4, 6, 8, 10, 12, 14. We got to go up to 19. So 1, 2, 3, 4. That would be 18. One more, 19. And that would be the diagram for F2 minus. Now that's a big mess. So what does that even tell us? Here's what it tells you. 2 important things. Remember, bonding orbitals stabilize the molecule or ion. Antibonding orbitals destabilize it. So the issue here is how many electrons do you have in bonding orbitals? How many do you have in antibonding orbitals? They cancel each other effectively. So if you have 2 electrons in bonding orbitals and 2 in antibonding, the net is 0. You don't have any net bonding. The 2 destabilize as much as the 2 stabilize. So here's what we do. We do a calculation called, bond order. I almost called it formal charge. Bond order. Okay, here's how you calculate it. You add up all the bonding electrons. So you add them all up. Then you add up all the antibonding electrons. Then you take that difference and you divide it by 2. Why divide by 2? Because we're talking about a bond. Essentially, we're calculating how many net bonds there are in the molecule. A bond has, by definition, 2 electrons. So you divide it by 2 to figure out how many bonds there are. So for example, if I had 4 electrons, that's 2 bonds. Okay, so that's called the bond order. The larger the bond order is, the stronger the bond. The smaller the bond order, the smaller the bond. It is possible to get fractions. So don't worry if you get a fraction here. You can have 2.5 bonds or 1.5 bond or half a bond. Half a bond is weaker than a single bond, but stronger than no bonds. Okay, I've never seen a third of a bond or anything like that because you're dividing by 2, so you're going to get fractions of 2. So let's take a look. The number of bonding electrons, you just count up. I'll put this one in red. You just, actually, let's use it. Oh, I guess we'll use green. You just count up the ones that don't have the asterisk. Those are the bonding. Those are bonding right there. Right? All the ones that don't have the anti-star. So how many are in there? 2, 4, 6, 8, 10. So it looks like you got 10 bonding electrons, and then you subtract the antibonding. The antibonding are these ones, the ones with the star. Okay, so it looks like you got 2, 4, 6, 8, 9. Okay, divide it by 2 to get the bond order. So 10 minus 9 is 1. Divide that by 2, you get a half. 0.5. So the bond order for this one would be 0.5. Okay. There's a second piece of information. That's a weak bond, right? And it turns out F2 minus is not that stable. So it's easy to break that bond. And the reason it's easy to break that bond is because it only has 1 extra electron bonding compared to antibonding. Okay. So here's the issue now. The second thing is what they call magnetism. You can tell whether this substance is magnetic or not. So if you have unpaired electrons, it's called paramagnetic. And what that means is this thing, if you put a magnetic field, it'll be attracted to the magnetic field. So if you put a magnet next to it, it'll be attracted to it. In fact, liquid oxygen does that. Gases can't do it because they're moving around too fast and they're not condensed. But liquids and solids can show this phenomenon. They can be attracted to a magnet if they have unpaired electrons. So this particular ion, it has an unpaired electron right there. That's unpaired. So this thing is paramagnetic. Okay, just one. If you have 1 or 2 or 3 unpaired electrons, it's paramagnetic. Then there's something called diamagnetic. Diamagnetic means that it has no unpaired electrons. Every electron is paired, and it's actually repelled by a magnetic field. It's actually repulsed. So if you put a magnet next to it, it's actually weakly, it's not real strong, but it will actually move away from the magnet. So paramagnetic attracted to the magnet, diamagnetic repelled by the magnet. Okay, paired versus unpaired. If there are no unpaired, if everything is paired up, it's diamagnetic. If there's even one unpaired electron, it's paramagnetic. So let me show you another example. Let's see, let's come over here, show another. So just so you know, it looks like they're having you do ions. They want you to do ions. Sometimes they're not ions, okay. So I just want to do one that's as different as I can. Okay, let's do this one, N2, Ne, this one's crazy, right? Ne2 plus, okay? Now, this is in group 8A, okay? So that means you're going to use the second one I showed you, the one that is 6A, 7A, 8A. Remember, there's two diagrams. One for groups 1A through 5A, and then the second one is 6A through 8A. Okay, so let's take a look at this one. So this is interesting. So this is group 8A, so it's the same diagram as we just did with the F2 minus, right? Because that's in group 7A, this one's in group 8A. So let me, oh, I have it right here. Okay, so let me draw it. So 1, 2, 3, 4, 5, and then you get 2. And then you get 1. Okay, so sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2p, pi 2p, pi star 2p, sigma star 2p. Okay, wow. All right, good. All right, now again, the way Alex set this up is they're going to have you do all the electrons. So don't fall into the mistake of doing just the valence electrons. Sometimes what people will do is they won't show the core electrons. So they'll start right there. They'll just start from here. If you're doing that, then you can just use valence electrons. That's perfectly fine. But if they show you all the way down to 1s, use all the electrons. So neon is in group 8A, so it has 8 electrons. But there's 2 of them. So that's 16. And then it's a plus. This is an anion, a cation ion. So subtract 1. So it's 16 minus 1, 61. 16 minus 1, which is 15. So in general, there's 3 things we want to be able to do. One is fill out this diagram, spin up, spin down, all that. 2, do the bond order, bonding electrons minus antibonding electrons divided by 2. And then 3, paramagnetic or diamagnetic. Any unpaired electrons, it's paramagnetic. No unpaired electrons, it's diamagnetic. Okay, so we got 15 electrons. So off-bow principle, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Is that right? Yeah, I guess that's right. Oh, because it's plus, right? So it would have been 16 if it was just Ne2, but it's Ne2 plus. So it's right there. Okay, there we go. Okay, so we've done the diagram. Now the next thing is let's do the bond order. Okay, so bonding electrons minus antibonding electrons divided by 2. And it's okay if you get a fraction. Sometimes you do, sometimes you don't. If you get 1, it's a single bond. If you get 2, it's a double bond. If you get 3, it's a triple bond. But you can have half bonds, okay? So nature's more complex than Lewis structures, right? We didn't talk about half fractional bonds in Lewis structures, but nature's more complex than that. So let's count up our bonding electrons, subtract the antibonding electrons, and then divide it by 2. So bonding electrons, I'll do those in blue, I guess. I guess we'll do it in green. So bonding electrons are the ones that don't have the asterisk. Okay, so you count them up. 2, 4, 6, 8, 10. And then let's do the antibonding in red. The antibonding are the ones that have the star. 2, 4, 5. Did I do that right? 2, 4, 6, 8, 10, 12, 14, 15. That doesn't seem right. Oh, I'm sorry. I made the mistake that I just told you guys not to do. I said it was in group 8A, so that's 8 electrons. Big mistake, right? What I said was, if you're starting at 1s, that means you're including the core electrons. There's 4 electrons there. So neon, even though it's in group 8A, it's actually element number 10. My mistake. So it's Ne2, so that's 2 times 10. And then it's positive. So now you subtract 1. So that's actually 20 minus 1, which is 19. I'm sorry, my mistake. 19 electrons. Okay. So let's come back to the beginning. 19 electrons. So 2, 4, 6, 8, 10, 12, 14, 15, 16, 17, 18, 19. There we go. Okay. 19 electrons. So now that's going to change our bond order calculation. Okay. So the antibonding, really what it's going to do is going to change the antibonding. Glad I caught that. These are all antibonding right there. Okay. Those are all antibonding. So really, it actually looks like it didn't change the number of bonding electrons. It just changed the number of antibonding. So bonding is 2, 4, 6, 8, 10. So that's still 10. But what that's going to do is it's going to make the antibonding a lot more. So the antibonding will be 2, 4, 6, 8. Oh, sorry. Plus this one, 9. So 10 minus 9. Okay, so now that makes more sense. I was trying to figure out, that did not make sense to me. So that's 10 minus 9 over 2, which is 1/2, right? So again, your bond order for this one is 1/2, right? Now let's do the paramagnetic versus diamagnetic. Okay. If it has any unpaired electrons, it's paramagnetic. It's going to be weakly attracted to a magnetic field. So there's an unpaired right there. It has 1 unpaired. So it's not going to be really strong. The more unpaired electrons you have, the stronger the attraction is to the magnetic field. But if you have any, it's going to be attracted to a magnetic field. So that means it's paramagnetic. There's 1 unpaired electron. If we were to try to do Ne2, just to kind of show you the difference. What's the difference between Ne2 versus Ne2 plus? This has an extra electron, right? Because you don't take the 1 away. So instead of subtracting 1, you don't subtract that one. So this one actually has 20 electrons. And where would that 20th electron go? It would go here, right? That's the next orbital. By the way, there are orbitals up here. We're just not showing them. There's like 3 and 4, but we're ignoring those. We don't have to worry about those. If you were doing advanced experiments, you would have those too. But that 20th electron would go right there. And what would happen? It would essentially change this number to 10. 10 minus 10 is 0. Bond order would be 0. And it would ruin any magnetism, right? It would change it from paramagnetic to diamagnetic. But here's the important thing. If you have Ne2, which has 20 electrons, the bond order is 0. So the molecule doesn't exist. It's unstable. At least it's not any more stable than the individual atoms. And that's because it would have just as many antibonding electrons as it has bonding electrons. So what do we know about noble gases? Ne2 doesn't actually exist in nature. People have tried to make it. And what you can find is that if you cool it down, you can make it kind of form, but then it just breaks up. It's unstable. And so the reason for that from molecular orbital theory perspective is that you have just as many antibonding electrons as you have bonding electrons. So there's no reason for it to form. But Ne2 plus, now you say, well, what about Ne2 plus? What if we could take an electron off? Would that form? And it turns out it does. Ne2 plus does form. You can make that. Again, it's not real stable, because essentially what happens is if it finds an electron from anything, it'll take that electron and then make it Ne2 again, and then it breaks up. But for that period of time where it doesn't have that extra electron, Ne2 plus does actually form. You can measure it, and it's because it has more bonding electrons, just by one, than antibonding electrons. It has a weak bond. It's not real strong. It's half of a bond order, but it is there. Okay. So when you do these, just be careful. Make sure you use the correct diagram. This is the diagram for 6A through 8A. The one for 1A through 5A is just slightly different. Essentially what happens is this, I guess it's this guy right here, just jumps back down there, I think is what it is. Is that right? Yeah, so it's just a minor difference. But make sure you use the right diagram. Off-bow principle. And then when you're in the pies, just make sure you use the spin up, then spin down, spin down. That's Hund's rule. So all of those rules are there. Okay. That is the end of chapter 9. That's our end of our chemical bonding stuff. So we went through a lot, right? Chapter 8's a lot of stuff about, Lewis structures, formal charge, resonant. Your exam, most people haven't taken the exam, so your exam is going to be on formal charge, resonance, and Lewis structures and bond enthalpy, right? That's all chapter 8. But this stuff from 9 is very interesting stuff, and it leads into organic chemistry. So if you go on to take organic chemistry and biochemistry, that's where this stuff really becomes important. Okay. So very good. So that's the end of our meeting here. And reach out to me if you have any questions. I just have, I did grade the periodic trends experiment. So this weekend, I'm going to grade the carbon dioxide, the molar volume of carbon dioxide. There's one more lab report you need to do, which is spectrophotometry. So that's uploaded now. That one's a little different in the sense that you don't have a separate procedure from report sheet. The procedure and the report sheet are all the same one. So there's just one document. It's a Word document. So you're just going to, type your name on it, fill in the answers, and then you submit that one, the spectrophotometry. Okay, so no, it's not separate there. All right, and then that'll be it for the labs. Okay, so next week, I don't have any lectures scheduled because it's actually finals week. So if you want to have a Zoom meeting, if you're going over questions, you want to do a Zoom meeting, just get in touch with me, contact me. I will be available for office hours next week. And then essentially as people start taking the last exam, I'm going to start grading the last exam as soon as I can so that it's not pushed off to the last minute. Okay. Very good. Take care, everybody.
Thank you, Professor.
Thank you.
Au revoir.